Stanford University.
Here we go. Oh, there you are.
Welcome to 380. We are charging rapidly through the quarter. Next week's speaker, Mike Flynn, is an old friend of AA380. He was also a Stanford professor for many years. If I recall correctly, one of the theses that he supervised established that the maximum size of a one-cycle cache is bounded if you're pushing all the limits you can push. That sort of very relevant for today's talk. One of the common statements in computer science is, it's turtles all the way down. One of those turtles turns out to be distributed systems. We all know that distributed systems span buildings, continents, and other such geographically large things, but thanks to our friends in device physics, single chips are now distributed systems and have been for some time. Today's speaker, Volker Strumpen, has worked on one of the largest distributed systems, Akamai, and has now turned his attention to, perhaps equally important distributed system, on-chip caches.
Thanks a lot, Andy. Yeah, let me begin by acknowledging a few co-workers, a subset of those who have been working with me on the Spider cache. First of all, Matteo Frigo, with whom I started this project almost 5 years ago when we joined IBM's Austin Research Lab. We came up with the basic ideas and the basic design. Then it went dormant for almost 2 years, and Fadi Jababa and Jeremy Chow, two of our hardware designers, picked up on the idea. And at that point, we actually designed it all the way into hardware, and we have a prototype, a proof of concept prototype of the Spider cache by now. So this is actually real stuff. Let me begin, with a different button. No, that does it too. Good. By stating the problem that we are trying to tackle, and I got more problems on my hand than I can. Okay, I do not see, don't send.
Don't send.
All right. Okay. All right, so the problem statement. The problem that we are facing these days in semiconductors is that the distance a signal can travel across a chip within one clock cycle of the global clock frequency is decreasing rapidly. And these two die shots of power PCs, the power 5 on the left, the power 6 on the right, illustrate that problem very vividly. The power 5 and the power 6 have their L2 caches highlighted in blue, and the L3 caches in red. They are off-chip for both chips. And the important piece of information is encoded in the yellow circle segments, whose radius is the distance that a signal can travel up through optimally buffered metal wires on the chip. On the power 5, we were able to almost traverse the side length of the chip. On the power 6, it's barely 10% of the side length. Now, that's obviously a problem for memory designs, which we like to be large and fast, but if we stick with good old physics, we won't get there.
So it's not photons?
It's not photons in this case.
What's the speed of light out of chips on the surface?
I'm going to show you.
You've got it already. I'm not sure.
Good you asked that question.
All right, let me start with the one on the left first, though. This is a different perspective on the same problem. It shows the delay of a signal over the larger of the dimensions of a memory array, in this case an SRAM memory in a 45 nanometer process. Okay? And drawn are two curves for two different metal layers, and annotated at the nodes are the array capacities. if you pick some delay, say 200 picoseconds, which is equivalent to a clock frequency of 5 gigahertz, you can see that we are barely capable of traversing the side length of a 256 kilobyte array, which is nothing by today's memory standards. Okay? The slightly bleaker picture emerges if you look at the trend of the ratio of the propagation velocity to the speed of light, namely the slowdown of a signal relative to the speed of light over different technology generations. For the 130 nanometer node, we see that we got almost within a factor of 10 of the speed of light, but since then, the propagation speed has been slowing down. Okay? In the 32 nanometer process, we are giving up basically a factor of 4 compared to the 130 nanometer process due to parasitic capacitances, mostly. Okay? So the picture is not getting better.
We should call it relativistic effect. In misnomer.
I leave that to you. All right, so here is what we are proposing. This is a kind of executive summary. I filled in the details during the remainder of the talk. We propose a self-organizing cache architecture, the Spider cache, to offer scalable performance for large cache capacitances and high clock frequencies into the physical limits with theoretical guarantees. Okay, this picture gives you a cartoon of how we envision a single chip design to look like in the near future. You may have a bunch of processor cores, 16 here in the upper left corner, and the rest of the chip will be memory. In this case, this is a spider cache consisting of individual memory tiles, memory arrays from a VLSI perspective. And those tiles are sized such that the propagation distance or the propagation speed across one tile is matched with the access time within the tile. Okay? So the engineer has a knob to size a spider cache according to timing and other constraints by determining the tile size. Okay? And that will, in the end, scale into the technological and physical limitations if you assume that one bit will always occupy a finite amount of space and propagation velocity is bounded by the speed of light, etc. Now, the main problem that you have with such a design is how do you place data into individual tiles? What you would like to do, you would like to have the data as close to the processors to minimize the access time. Okay? And what I will try to show is that using what's called the move to front heuristic is a provably effective way of performing this particular type of placement. And dynamic replacement, namely moving cache lines around through those tiles. At the same time, this particular design consisting of n tiles behaves like an n-way set associative cache, however without explicit bookkeeping. You don't need counters to account for least recent use, etc. Also, and more importantly on the distributed systems front, it's not really a distributed system with a network, it's a systolic pipeline. It's a memory that allows you to keep multiple accesses in flight, thereby giving you high throughput without the overheads of a dynamically routed network or excessive buffering needs. Was that the right button or not? Okay. That's a goodie. We have a problem. Did the machine hang itself up? It's probably, let me try this one. Ah, yes, the mouse works. Okay. The buttons stop working, the mouse works. Okay, the rest of the talk is structured in two parts. In the first part, I want to review memory design with a particular focus on placement algorithms in the spatially distributed designs. And in the second part, I introduce the spider cache and show some performance numbers based on full system simulations. Now if I can just hit that tiny little box. Okay. Let me begin by just recapping the traditional conventional memory hierarchy. Okay, here we have typically in every microprocessor these days a processor with a register file, and L1 cache, L2 cache, many cache levels, DRAM, disk, the network, and so on. From my perspective, and topologically speaking, this is, however, nothing but a linear array. It's technology friendly and economic and has wonderful properties, but it's a linear array. Okay? Because these caches here get bigger in the hierarchy, they suffer from larger wire delays, and for that reason we put in more levels from generation to generation. To speed things up, we furthermore tinker with all kinds of tricks: associativity, prefetching, speculation, pipelining of directory and data lookups, and so on. What I'm trying to say is it's time, given the technology, to move on and leap towards a spatial memory model where we view a memory cell as a piece of physical hardware that has a physical extent with a width associated with it. Okay? And what we do is we design a memory as, in this case, a very simplistic linear array connected to the processor on the left. And now we try to account for access latency in terms of distance from the processor. Right? Now, to make that accounting simple, what I do is I assume that the distance of the cell from its processor is its index. Okay? Cell 7 has distance 7. Normalized to the width. I also assume that a signal can travel across one cell within a single clock cycle, which I can easily do by adjusting the width. And now I measure the access latency as the propagation round trip time as 2 times the cell index. So in this case, the access time to cell 7 is 2 times 7 equals 14 clock cycles. Now let me use this simplistic model to study a few placement algorithms. And the first one is the widely used direct mapped placement used in caches everywhere. You interpret the least significant bits of your memory address as the index of the cell where you place your data. In this case, for example, address A happens to map into cell 7, B into 10, and C into 2. Okay? At this level, you have absolutely no control over the distance from the processor. Now you could say the programmer could optimize that address mapping by allocating the data associated with addresses A, B, and C to addresses that map closer to the processor, or you may ask your almighty compiler writer to do it for you. Okay? The point here being that neither is desirable nor necessary, and we're going to see that in a few minutes. Okay. Back to the example, let's assume we have a program trace, a memory trace that generates these load instructions and account for the total latency of the program execution. On an initially empty cache, we will, when executing the first load of address A, incur a cold miss, have to go out into memory, fetch address A, place it into cell 7 based on the least significant bits, and then incur an access latency of 2 times 7 equals 14 clock cycles. The same thing with B and C and so on for the total latency of 82 cycles plus the 3 memory accesses that I don't detail any further. Now this doesn't work either any longer. What? Yep. Okay. Sorry for that. Okay. So the direct mapping is obviously a little naive, let's try to be a little smarter. Okay? The first thing we observe is that addresses are accessed with different frequencies. So if we have our trace, why not map the most frequently accessed address closest to the processor? The most frequent first placement heuristic. In this case, B is accessed 3 times, most often in this trace, map it into cell 1, C 2 times, map it into cell 2, and A only once into cell 3. And then by the same mechanism than before, we get a latency of 20 cycles, which is 4 times better than in the previous example, and therefore apparently superior, and you might think this is the best you can do. Unfortunately, we are not oracles and don't know the access trace in advance. Okay? So, lacking the knowledge of the access frequency, we need to resort to different tactics, and the best one that is known is a dynamic strategy that is provably within a factor of 2 of the best static strategy that knows the entire future of the access trace in advance, like the most frequent first on the previous slide, and that is called move to front. And the move to front heuristic has a deceivingly simple recipe. Whenever you access an element, you move it to the front of the array. In this example, this plays out as follows, and now I have the problem of having to click the button a bunch of times, so I just do it from here. So in the first access, we miss on A and move it into cell 1. Okay? Then we incur 2 clock cycles of latency. B, we do the same thing. Cold miss, we go into memory, move it into cell 1, but hold, A is occupying cell 1. What do we do with A? We push A back. Okay, assuming that pushing A back can be overlapped with a memory access to get B, we don't account for additional latency, but the 2 cycles to get B into the processor after having moved it to front cell 1. Same thing with C. Now we push A and B back to get C into the front. The next access to C is fast. It's the minimum latency of 2 cycles because C is in the front. To get B, we need to go all the way out to cell 2, which incurs 4 clock cycles latency. But now we move B to the front, push C back, closing the hole that we left by moving B out of 2. Okay? Incurring a latency of 4 cycles. Now B is in the front, incurring another 2 cycles latency for a total of 14 cycles latency. Note that 14 cycles is less than the 20 cycles that the most frequent first placement incurred. Okay? And all that by looking at one access at a time as opposed to most frequent first, having complete knowledge of the entire trace. That's pretty amazing.
Aren't you ignoring that they had to be somewhere to begin with? Like you're just magically creating them all in slot 1.
Plus memory access.
Plus the memory access.
Oh, okay.
They all have 3 memory accesses, all examples. Okay? Wherever they are.
Yeah, okay, you're right.
All right? Okay? So let me show you the effectiveness of move to front in a more realistic setting. Okay? This is a 16-tile spiral cache where each tile is now not just one datum or one cache line, but each tile is a 128 kilobyte direct mapped cache for a total of 2 megabyte capacity. And we run a matrix multiplication and a randomized quicksort algorithm on this memory structure. Let me focus your attention on the hits columns. The hits show you how often one tile has served a datum in response to a request from the processor. And the first thing that we observe is that the vast majority of all hits come out of tile 1. In fact, if you look at the quicksort, it is truly amazing how many data are served out of tile 1. Okay? You kind of can interpret an exponential slowdown or an exponential distribution into this hit distribution towards the end of the linear array. Okay? In order to characterize this behavior, you can calculate the average depth that you need to search into the array before an access is actually served. And the bottom row shows you that depth. It's just 1.26, 1.27 tiles into the array. Okay, in other words, the move to front heuristic is so effective that virtually all of the accesses get served out of tile 1. You hardly ever need to search any deeper. Okay? Another observation that I want to make on this slide is if you look at lines 15 and 16, tiles 15 and 16 at the end of the array, there are 0 hits there. That's not an accident, that's because I picked the working set of these algorithms to fit snugly into this cache. The most important point here, however, is that it illustrates that the move to front heuristic compacts your working set at the head of the array. Okay? It's easy to view this intuitively by noticing that whenever you move something out of memory into the front, you move it into the front, push something else back, everything is nicely compacted at the front. Whenever you move something from inside to the front, everything that gets pushed back to make space for that element will close that hole that you left by moving it out. Okay? So because of that compaction effect, you can easily partition your spider cache into 2 parts. The active part at the head of the spider that actively participates in the program execution, and the tail that is totally inactive. Nothing is happening there. And that compaction effect is easily detected dynamically with a little piece of hardware, and you can use that as a knob to switch off all the tiles at the tail to do power saving. Don't burn leakage power if you don't have to, and that enables us to build huge caches where a small working set does not charge you the penalty of leakage power just because it's a small working set. All right? Okay, one more word about the move to front heuristic. It's by no means new, just the opposite. In the late 70s, early 80s, there appeared a gazillion of empirical papers on managing a list. And the move to front heuristic was one of those that found particular interest because it was very effective in practice. However, it got a real boost when Sleater and Tarjan formulated a theorem, actually developed the potential argument as a proof method to prove this theorem that I'm quoting informally here. On any sequence of operations, means insertion and lookup, move to front is to within a constant factor of 2 as efficient as any algorithm, including offline algorithms that base their behavior on advanced knowledge of the entire sequence of operations, like most frequent first, okay? Provided that the cost function for accesses and insertions is convex. This technical condition here at the end, the spider cache observes. And in today's computer science lingo, we just call this too competitive. It's a competitive analysis that says that there is no other heuristic that can perform better than a factor of 2 than move to front. Okay? Now, that doesn't mean that a cache with a move to front heuristic as a placement strategy is the super thing. It will run everything fast. If there is a poorly performing application, the move to front heuristic will not perform a factor of 2 worse than what you can do otherwise, but that otherwise may be outrageously bad. So the move to front heuristic will not speed that up unduly. Okay? If you stream data through the cache without any temporal locality, the move to front heuristic cannot help you, and no cache can help you. Okay? So the bottom line is we use the Sleater-Taujan result with the move to front heuristic as placement strategy, and that enables us to claim that there is no other distributed cache architecture that can be faster than a factor of 2, or let me be a little more lenient, faster than a small constant factor. We lose small constant factors everywhere once we do the hardware design anyway. Okay? So, but there is no other cache architecture that is faster than a factor of 2 small constant factor than the spider cache. Right? Okay, now let me introduce the spider cache first by overviewing the key ingredients. Okay? We have already talked about the tiled systolic architecture. Now, in this case, the spider cache employs fast direct mapped caches. You can replace that by fast two-way set associative caches if you like. If you have a k-way set associative tile cache and a cache with n tiles, the overall cache will be k times n set associative. Okay? It's a pipeline design, and I will fill in some more details about the pipelining. It's associative, mostly because it can be shown that the move to front heuristic, from a perspective of competitiveness analysis, is equivalent to LRU, least recently used. Okay? However, it does not require explicit bookkeeping. On the other hand, it requires moving data around across tiles. The move to front heuristic gives us the provably competitive placement strategy. We exploit the dimensionality of space. So far we have only seen one-dimensional linear arrays, but for a general k-dimensional spiral, I will show you that the worst case excess latency is the kth root of n, the number of tiles. And the power efficiency stems from the compaction effect that I mentioned earlier already. Okay, how do we arrive at a spiral design? Remember the linear array. Let's say we have 49 tiles in that linear array for a worst case excess latency of accessing the last tile, 49, of 2 times 49 equals 98 cycles. Okay? Now let's see what 2D can do for us. Wrap the spiral tile 1 by its head and roll it up. And what you get is an Archimedes spiral in Manhattan layout, the blue line. Okay? Now what we do is we assign one functionality to that blue line, which we now view as a point-to-point network connecting neighboring tiles. And the only thing that it's going to do is implement the pushback functionality. Okay, whenever we fetch an element, we push data via the spiral backwards and use a second network with the small black arrows here, the move to front network, to fetch an item. Okay, so in the worst case, the tail end tile 49 is in the top left corner. We now broadcast a request across the diagonals to the outer corners. The request will find the item in tile 49, and then we XY route the response back to tile 1 via tiles 48, 47, 46, and then down to tile 1. Okay? The number of hops that takes from 1, 9, 25, 49 back to tile 1 is 10. And 10 happens to be the square root of 100, and 98 was the propagation delay of the linear array. So we've just reduced the worst case access time, the worst case to the very last tile, from n to square root of n. You can do the same thing in a three-dimensional design. Right? You then need to snake the spiral in 3 dimensions. Martin is going to do that for us.
It all flows.
Right. Now, intuitively, the effectiveness of the move to front heuristic now comes from the spiral network keeping data that you push back for as long as possible, as close as possible to the processor. Okay? If you move something out of tile 1 into tile 2, it's one hop away from tile 1, and it stays one hop away until it moves from 9 to 10. And then it's 2 hops away from tile 1 for a long time of pushbacks. Okay? Now, of course, we don't want to incur the worst case excess delay, even though it's only square root of n. What we want is exploit the move to front heuristic and exploit getting an item out of tile 1 most of the time. So we don't want to send a request all the way out to the corners every time. And in order to get a short access time, most of the time, we employ a geometric retry. Okay, here quickly recapped by means of a linear array. It works as follows. The processor first sends a request to tile 1. If it hits, it returns it, you incur a minimal access time of 2 clock cycles, you are done. If not, the processor retries. It doubles the retry radius to 2 for 4 cycle latency. If it doesn't find it there, it doubles it again, and so on for multiple retries through this entire structure. The worst case without the retry is 2 times 16, forth and back, is 32. With the retry, it's less than 2 times the worst case, less than 2 times 32, in this case, 62 cycles. Okay? The geometric retry has a wonderful capability of only increasing the worst case excess by a factor of 2, but it gives us the big advantage that whenever we find an element in the very front, we get it there fast. And the move to front heuristic helps us doing that. Okay, in 2 dimensions, we implement this just by controlling the radius that a request travels out on the diagonal. The first one with radius 1 just looks into tile 1. The next one goes out by a doubled radius of 2 to tiles 3, 5, 7, and 9, and then communicates in an XY fashion back to tile 1. And lastly, it goes out all the way and searches all tiles. So the request goes out, and then on the way back, it searches all the tiles, and hopefully one of them finds the item and carries it back to tile 1. And this systolic communication pattern is, by the way, communication-free, although they are join points. They are join points, but you always have the same address in a request joining at the same time, so there are no real collisions in this design. You don't need buffering. Okay, let me give you a perspective from within one tile. Within one tile, you have, in our case, a fast direct map cache. You have the 2 networks, the pushback spiral network and the move to front network. At the tile, you have an input and an output. You have the tile control logic coordinating the actions depending on what's happening on the networks. And the registers here shall demark the tile boundary to the next tile. Okay? There are 3 actions that can happen to a tile. Number 1, a pushback, or from the perspective of a tile, a push-in arrives on the spiral network. That is a packet because the processor has requested a move to front and tries to make space by pushing things back. Okay? We get the address and the data via that network. And now the control logic does the following. If the address in the cache is valid, it reads the current data in the cache out and pushes it back to the next tile in the spiral, and then overwrites that line in the cache with the new incoming data. Okay? If the data in the cache is invalid, the other of the 2 cases, it just overwrites the line with the incoming data filling a hole. Okay? You can imagine that the pushback is now pipelined on all the tiles through along the spiral network In the worst case, if there is one pushback per clock cycle from the processor, everybody is swapping its data back into the next tile until there is a hole, and that's where the pushback stops. That's the compaction, part of the compaction effect. Now, the other action is that a move to front signal arrives, and there are again two possibilities. The data arriving in the move to front packet can be valid. That means it has been found somewhere in the outer realms of the cache already, and the control logic just passes it through towards the front, tile 1. If the data is invalid, the control logic does a lookup in its cache and sends the data together with the valid bit towards the front. If the data bit, the valid bit is valid, then it has found the data and everybody on the way to tile 1 just passes them through. If the data bit is invalid, everybody on the way towards tile 1 needs to do a lookup until it's found, or not at all. The third action that can happen, or that has to happen, is to communicate with the neighbors. And that communication is important because we want to exploit the wire length. And I'm going to look into more detail into that aspect in the next slide. Before I do that, though, I might want to remind you that a direct map cache implemented in a conventional fashion typically has a separate read and a write port. Okay? So the pushback operation here, which requires a read and then a write, although it's to the same address, would typically take 2 clock cycles to implement, unless we change the array implementation and implement a swap that actually reads and writes the data to the same address, sharing the address decoding effort. Okay, in the following, I assume that we have such an optimized cache that can do a pushback swap and the lookup due to the move to front, each within 1 clock cycle. Now, what we really want to do is we want to utilize all the wires in our design most efficiently. The wires are our precious resource. To the very first order, as a back of the envelope calculation, consider what we do if we have a memory interface in the center of the bottom of a tile, then communicating with the neighboring tiles will always take 1 side length. Okay? The actual lookup, the access within the tile, will take 2 side lengths, 1 side length to do the address decoding and another one to do the word line sensing. Okay? Fair enough, factor of 2 between the two is not too bad, but now we can actually pipeline the communication with the actual cache lookups. We always need to do a push swap and a lookup, okay? And preceding the push swap cycle, we communicate the pushback data across the wire. During the push swap, communicate the move to front data, and so on. Okay, so with such a design, we would actually achieve a wire efficiency of 75%. Now, you can imagine that you can improve on that, for example, by moving the memory interface into the center of the tile, blocking the cache, then reducing the access time within the cache that way, and getting closer to a 100% utilization. That's now a matter of design effort for the cache within the tile. All right, back to the big picture. We call the spiral the Archimedes spiral with front tile 1 in the center. That's not a particular good location for a system layout, okay? Unless you have 3D technology where the processor can communicate immediately with a center tile, you will always incur the latency to cross half of the side length to get to tile 1, okay? So in order to get a better layout and accessibility to the front tile, we can now engineer the spiral network to still maintain the property that for most of the cycles, the data will stay as close to the processor, In this case, it looks like an electromagnetic pulse in Manhattan laid out, moving outwards in that quadrant. Okay? And now we have access to Taiwan. You can put processor memory interfaces everywhere around here, the bottom left corner of this quadrant design. Also, what I'm showing on this slide are the timelines that illustrate the pipelining. When this cache is actually operated in full throughput mode, the processor will send a request up on the diagonal, one per clock cycle. So each of the diagonal is one pipeline stage. Then at the very end, it turns around, and on the way back during each clock cycle, the same request will visit all the tiles on one of these timelines. Okay? So this cache has how many pipeline stages? 8 on the diagonal, and then 14 of the blue timelines going back, for a total of 22 pipeline stages. So this cache is capable of maintaining 22 requests in flight and delivering one response per systolic cycle, which is probably 2 clock cycles to implement the cache exercise. Right? And with that one quadrant design, you can now build space-filling spiral caches. Okay, take the one quadrant, reflect it over the x-axis. Taiwan is now on the center. In the center, on the left, you can put a processor to the left, and the right of your die is your spiral cache. Or 3 quadrants, one, reflect once, reflect again. And you can put processors in the top left quadrant. This is the design that I've shown you in the first slide. Okay, this is how this degenerate-looking, not like a spiral-looking blue network comes about. Or you build a 3D design. This is one octant of a 3-dimensional spiral, where the diagonal now goes out on the 3-dimensional. You may not be able to see this line, I'm not sure. It goes out across the diagonal, and the timelines are now time planes moving backwards to Taiwan, color-coded here. All right, last but not least, a few performance experiments. We actually implemented a cycle-accurate register transfer level model of the spiral cache and plugged it into our full system simulator. So all the results, all the clock cycle numbers you're going to see are now numbers resulting from experiments where we boot Linux, switch on the timing, run an application, end the timing, and measure the number of clock cycles. And I'm going to show you a comparison of a conventional Power 4 memory system with a Power 4 processor, actually, 4+, that has a 32 kilobyte L1 with 1 clock cycle latency, array latency, okay? An L2 of 512 kilobytes with 4 clock cycles latency, and a DRAM with 67 cycles latency. This is a design that does not assume a power bus in between the memory, between the processor and the DRAM. Otherwise, that would be 400 cycles to go out there. Okay, it assumes that the DRAM is directly connected to the processor. In the spiral configuration, I replace the L2 cache. I leave the L1 caches in there. Okay? And that is because I want to mask the 2 clock cycle per systolic cycle latency to the processor. Okay? But the L2 cache I replace with a small 4x4, 1 quadrant spiral cache design of 2 megabyte capacity, means 128 kilobytes per tile, and a line size of 128 bytes, which is the typical PowerPC line size. Then the first experiment is, oh gosh, can you see those curves, the red one? Okay. Okay, good. So the first experiment is a simple synthetic benchmark. It measures the latency of excess latency. It's a simple loop that repeatedly loads n bytes with one load instruction per cache line, means it's twice by 128 bytes. And then we sweep over this byte size. And the red curve here shows you the conventional hierarchy, and it's the typical step curve that you're probably all familiar with. Up to 32K, we access L1, which costs us somewhere about 1 clock cycle. Then we access the L2, which costs us on the power 4 plus 8 clock cycle. There was an additional penalty to the L2 penalty. Apparently it doubles the access latency. And at 512 kilobytes, the L2 capacity, we jump out into DRAM and get about 67 cycles latency. Okay. Now the light blue curve here at the very bottom is the spider cache. Remember, we had a 2 megabyte capacity, so the spider cache jumps at the 2 megabyte boundary, but up to then it sits rather nice and flat here near the x-axis. I characterize it informally by saying that it knocks down the memory wall into a gentle slope. Okay? In fact, this shows you that the spider cache could be significantly larger, namely so large that you extend this curve until it transitions into the DRAM latency without a discontinuity. Okay? I don't know how big that would be. My simulation cycles were not good enough over the last 2 years to explore that design point. Okay. All right, so to figure out what portion of the benefit comes from the pipelining effect, I artificially throttled the number of outstanding responses into the spider. Okay. The green curve shows you just a single access in flight in the spider, and it shows you basically a step curve due to the bitwise. Okay. And it also shows you that I did not make any effort to hide the mislatency before a DRAM lookup. Memory interface in today's processors goes in great length into hiding the cache mislatency before doing a memory lookup. Okay? I did not do this. I don't need to do this because as soon as I allow 2 accesses to be in flight, the latency inside the cache goes down and my serial lookup latency into the DRAM is gone. Okay? And with 4 accesses, I'm already very close to the ideal spider, which, being a 4x4 design, has a pipeline depth of 10 stages. Okay? So this basically shows you all the information you need to understand how a spider cache behaves, essentially. Now, how does that translate into application performance? We programmed 10 applications that we deem important, 3 linear algebra applications, matrix multiplication, QR, and SVD, then a stanza computation, longest common subsequence computation, an FFT, the quicksort, and 3 graph algorithms, minimum spanning tree, shortest path, and maximum flow, a maximum flow problem. And for each of these, you see the number of clock cycles on the conventional system and the spider cache. The important information is in the speedup column, spider versus conventional, and we see that for about half of the applications, we get significant speedups between 1.4 and 3.4, okay, which are numbers that are distinctly different from typical ISCA architecture papers that twiddle in the 3 to 4% range rather than factors of 3 or 4. Okay. Equally important is that the other applications do not lead to a performance degradation. Okay. Here the access distribution of 4 of these applications. You see that things are not exactly exponentially tailing off, but you see that in Taiwan, the vast majority of all the accesses happen. Interesting here is the difference between the A1D cache and the SPIVER cache. Okay, the top row there shows the A1D cache hits. There are roughly 2 to 3 times as many hits in the A1D cache, the 32K A1D cache, than in Taiwan. Okay? But Taiwan has orders of magnitude more hits than all subsequent types, okay, which clearly shows you the difference of a memory managed with move to front versus a simple cache, direct map cache that doesn't know anything. Okay? There is a big qualitative difference. All right, let me summarize the features of the SPIVER cache. First of all, we think that it's a simple design. For another fact, with 3 of us, we designed one tire with a superset of all the network connections, replicated it, terminated the unused networks, and boom, we got a 4x4 tight SPIVER cache. Okay? Compare that to the design of a hierarchy of caches, where you got 50 designers, okay, or whatever many to design the different caches. Number 2, we get high throughput due to pipelining without compromising load latency. This is, in my eyes, a first. There have been many systolic memory proposals that always incur the worst case access latency by sending the request out to the boundary and then percolating, propagating back to the processor. We, of course, use the move to front heuristic to most of the time access the tile close to the processor, yet we can pipeline the accesses. Now, if there is a lot of throughput, means the processor issues accesses at a very high frequency, then your latency will go up because the pipelining will push requests farther out into the cache, causing them to return to the processor later, yet you get a high throughput of basically, in the best case, 1 access per systolic cycle. The whole design is associative. It's n-way set associative without bookkeeping efforts. It replaces the bookkeeping with the networks, essentially. It's scalable into the physical limits by tile sizing. The one knob that we give the engineers is to size the tile to meet timing and whatever other constraints. Our physical design studies show that the power density, despite all the data movements, is lower than that of a conventional L2 cache. And that is because there are not many movements. Most of the time we succeed in hitting in Taiwan. All right? Also, as I showed you with the simulations on the previous slide, we get quite significant performance gains, and that with a very small SPIVER cache. This is an asymptotic design for large caches, yet with 2 megabytes we get already rather decent speedups. And in conclusion, I think that the SPIVER cache is the best principled bet we have to tear down this freaking memory wall that we've heard so much about. Because of the move to front heuristic, we have a performance guarantee that allows us to claim that there will not be another cache design that can be by more than a small constant factor faster than the SPIVER cache. In fact, in all of our experiments, there has not been a single other design that was ever faster than the SPIVER cache. Okay. Our full system simulations have shown functional correctness and good performance, yet the simulation has one major drawback. We cannot explore the design space. The numbers that I've shown you plus another set for another processor, base processor, took 2 years on a bunch of machines. Okay. So I was hoping that guys like Christos Kozivakis would be able to do something like that on FPGAs. I don't see him around here though. And last but not least, we've taped out a first hardware prototype and are exploring a three-dimensional spyware cache with a capacity of about 50 megabytes. And with that, I thank you for your attention. Please.
What happens with multiple processors? Because the cache no longer is presumably shared, and yet you need to share locks in some place and other things. And you don't have the nice long linear path to each file, but you have some sort of chaotic graph, actually, particularly if the memory is shared.
So, very good question. Okay, there is a lot I can talk about here. Okay. So first of all, your presumption is only partially right. Okay, I can share the spyware cache amongst multiple processors if I want to. I don't have to, but I can. Okay,
and with real processors, anyhow.
Exactly. Okay, so first of all, consider a multi-programmed environment. Okay, one processor running multiple programs. The usual time sharing. All of the aspects, all of the properties of the spyware cache are preserved. The compaction will now involve multiple programs. Okay? We can still switch off all the tiles beyond the working set of multiple intermingled working sets. Okay? There is, if you do physical address lookups, no problem with distinguishing the individual address spaces. Of course, then you need to do the virtual to physical translation before you access it, etc., etc. But those problems are not different than with any other cache design. Now, if you start building parallel machines with multiple cores, my assessment here is that the spyware cache is the best bet to give you the point of coherence for a modest number of processors like you would put them on a single chip. Okay? Because of the pipelining, you get throughput. So if you interleave accesses from 8 processors, say, you can have them all in flight sitting in the spyware cache, and they can be served as if it was one of them accessing the spyware. You don't see a major slowdown out of that, right? So I've been playing around with system designs where you put 8 cores in front of a spyware. Each core has a small 32 kilobyte write-back cache that mask, as we saw on one of the application slides, about a factor of 2 or 3 of the accesses in the L1 cache. Okay? And then you need the bandwidth of the spyware cache to support the remaining write-back and load requests into the spyware. For a modest number of processors, this works perfectly fine. Okay. Now, if you want to have large numbers of processors, cache coherence protocols are not an option any longer if you want to scale. So what you do is you build a hierarchy of caches, or you have nodes with individual spyware caches that need to be kept coherent with whatever reconcile and flush and invalidate instructions that you need with any other cache design as well.
At some point, when you have increase the number of processors, a shared memory model no longer works well. And this, I think, actually buffers that rather nicely.
Yes, that's exactly my assessment of the situation as well. Right.
Very nice, very nice, very nice piece of work. Anybody else have questions?
Yes, please.
So far you're looking at this on chip, where I assume that all the memory cells are static RAM and they all run the same speed.
Yes.
Can you push this architecture all the way out to main memory?
absolutely. I would think that. What?
That's why we're laughing.
Somebody
before,
is
by the way.
flicking.
I think somebody else is pushing stuff out.
Yeah, I don't need the down. If I need it, I try to push the button. Originally, I thought the spider cache is the whole memory. Okay, you build your memory out of one spider. Now, engineering constraints like power consumption, leakage power in an SRAM, etc., basically prohibit that from being a sensible approach. Also, the 2-cycle clock cycle latency of the systolic cycle is potentially another factor of 2 that you don't want. So you may want to have an L1 cache sitting in front of a spiral unless you want to clock the spirals fast, twice as fast as the processor to mask that latency. So what you can do easily, of course, is use a spiral like an L2 as one level in a larger memory hierarchy, and beyond the spiral cache, you use the usual memory levels that you can imagine or that fit your system. So just as an option for a parallel system, I think the best solution is to use one spiral cache of, say, 50 megabyte capacity to feed a modest number of cores, 8, maybe 16, that each have a small L1 write-back cache and share the bandwidth into the spiral cache. You also want to have a bit of capacity in the spiral to get enough pipeline stages in there to get the proper throughput. Okay? This is a balancing act. And then beyond that, you implement a global memory address space with DRAMs that are distributed over the node of the machine. Okay? So I would say a typical parallel system has individual processing elements with a small L1 cache, fast L1 cache. Then you have a spiral cache for a modest number of cores. You consider that a node of the machine. And the node may have a partition of a global memory in terms of DIMMs, DRAM DIMMs. Okay? That's, I think, the most sensible memory design that such a spiral cache fits into. That doesn't really answer your question, doesn't it?
Do you want to push this all the way out to where DRAM is managed this way?
To the DRAM latency, right. You just need to make it large enough to match the DRAM latency.
Now
right.
we generally assume that DRAM is random access, which means we have to have the worst case time to the furthest place on the board where there's some memory. With this, you might be able to get around that and utilize the fact that it really is faster to get to the chips that are closer to the processor.
Oh, yes, absolutely. Right. So what you could imagine is build, I think I saw this somewhere, Sun was doing it. They were building a terabyte memory as a video server cache. Okay? I would build that as a spiral.
With no latency.
Yeah. Depends. If you have a whole bunch of movie frames sitting there in that terabyte, it's perhaps also a little bit of latency. And it depends on how many people are accessing that server to watch how many different movies. And it's not only bandwidth, it's also latency. In a parallel machine, latency is, of course, the big kicker. You need low latency. Bandwidth is also important, but low latency is much more important. So yes, you can, I think you can build, I cannot give you any proof of existence of such a design, but I can imagine that you build such a huge spiral cache and it can be effective for certain applications, perhaps such a video server.
Well, do you think the future of memory structures, in fact, will go to something like this, where the DRAM in the master memory, in fact, is not random access at all? The only size that it really deals with is that of the tile in the cache itself.
But you can also implement one tile with DRAMs, if you like to.
Yeah.
and the latency to travel between probably rather sizable tiles consisting each of a whole bunch of DIMMs can be masked by the same mechanism than here.
Rational to me.
I don't have any data on this. There's a speculation to the largest extent, please.
Well, if you check it out to what is probably the last stage in current systems, which is the paging file on rotating memory, now you have some interesting access issues with trying to do the move to front logic.
Yes.
Well, that's just because front keeps moving.
Yes.
That's just because you're using rotating memory. How long do you think that will
Using arrays.
The terabyte that we have for holding our digital photographs still seems to be the cheapest way to do it.
Right, but you don't random access that. You access
Right.
it file by file.
Well,
So you
we're
copy the file
the
in.
file's pretty randomly.
They don't have a paging file anymore on rotating memory, that's the point.
Well, I assume that you'll be a lot more efficient if you do the whole thing as a paging system rather than having a file system with completely different rules built in there that you have to move into the paging
They might just
system.
have-
I think this is rather independent of any paging. Okay, it's the usual separation between the operating system paging level of a system design versus the cache line based caching level that the move to front heuristic exercises.
Now, I worked on an operating system that did not have a file system. It treated everything as paging, and it got
Yeah,
a fairly
I
impressive
know that
performance as a
too.
result
Yes,
of that.
right. I don't think that's a good idea, but but yeah, I haven't thought through whether you can play these tricks unless you, for example, page entire pages, move entire pages around.
Yes, you have bigger cache cost.
Right. Yeah, for something like a video server cache, I would probably do that, design one cache line to hold a whole frame.
It's also more of an issue for flash memory, which isn't quite random
that
access,
too.
but doesn't
Right.
have the latency of
Right.
rotating machinery.
Yes. Yes.
We need better techniques for managing flash. We're emulating disk now, and that's the wrong answer.
Yes. Yes, that's correct.
Operating flash is expensive.
Twiddling pointers is not.
You don't want to write flash too often, so I would probably
Yeah.
not use flash memory for the individual types. No. But magnetic memory structures, for example, you could probably easily put into these individual types. Did you have another?
Well, I was going to say, with respect to that, the Intel X25 flash disks use a writing mechanism. It was described in a 380 of, about 6 months ago, I guess. But in any case, it seems to me that what we're evolving to is that more and more memory looks like a block device, and only stuff that's very close to the processors needs to be effectively random access. Everything else is a cache hierarchy in fairly large blocks. And as you get further and further away, blocks are going to get larger and larger. And that just is sort of the way the physics works, and we end up having to live with it. And it looks to me like that's actually fairly good for performance. And this particular caching scheme looks really attractive on a large number of fronts as far as I'm concerned. I think it's very interesting.
I can tell you one piece of information about a back-of-the-envelope study that we did of designing such a spiral cache with DRAM types. And that wouldn't work effectively because we would not be able to get the necessary bandwidth across tiles to match the high access latency within one DIMM, within one DRAM chip. Okay? You would need so many wires to get the bandwidth to move the data around to mask the latencies. Okay, that this design with DRAMs would be too slow to give you an effective wire utilization. Remember, what we are doing is basically the main efficiency optimization is you address, decode, and push data across the word lines while moving data from tire to tire. Okay? And with a DIMM that is very slow, you can have very long wires to move something across, which we don't need because we have this next neighbor network.
This
of
is
course.
assuming you're using commercial DRAM products, I presume.
Yes.
If
yes.
you make your own DRAM, you've
That's
got
a
lots of
difference.
bandwidth
Yeah,
inside.
like IBM's
Enormous.
EDRAM, for example, the spider cache would become effective if you have a minimum capacity of about 36 megabytes. And the tile size was, I think, something like 2 megabytes per tile for this thing to become effective. You need to amortize the stupid 2 clock cycles per systolic cycle latency. That forces you to give it a minimum size. With SRAMs, you don't really have that problem because they are so fast. Okay, with slow memories that have a latency, you basically need a minimum size for the memory before it outperforms a traditional hierarchy. It's an asymptotic design. In the end, the larger you make it and have an equivalent hierarchy with the same capacity, once you pass a certain threshold, the spider cache will become more effective than a traditional architecture.
Any other questions?
Yeah, for your full system comparison, you use a 2 megabyte spiral cache. How large was the cache in the like in the baseline system?
That was the same A1 capacity and the 512 kilobyte A2.
So couldn't part of the great speedups you get just be from stuff not fitting into the smaller LDs?
Oh yes, absolutely. Okay, this is comparing apples and pears. It's not an apple and apple to apple comparison. Yeah, but I have the numbers of the same sizes, and it looks pretty much the same than the numbers that I showed you here. Yeah, maybe I should have taken the numbers for the same sizes.
The cliff is
Good
just
point.
shifted over.
Yes,
That's all.
but yeah, good observation. All right.
Anybody else? Any other questions?
Say something about the 3D memory arrangements? How's that going to work out?
Okay, let's see whether I can click myself back in there. So does that work? Oh, the buttons work again. Okay, so this is one octant. It's the equivalent of one quadrant, okay? Where you basically take one quadrant and flatten it in one plane. Okay, so this is one plane here, and now you have 4 planes sitting on top of each other. The diagonal that in the quadrant design goes out on the diagonal now goes across the diagonal tiles from the bottom left corner to the top right corner. Okay? The networks that you see here within each plane are roughly the same than in the 2D design. However, it's only a subset of the connections that you need in the 2D design. The spider is not shown here. The spider you need to put in by connecting the subsequently numbered tiles, otherwise it would have been cluttering the picture too much. Okay? But the main point is, look at the move to front network. This is the move to front network, the arrows here. There are only these 3 connections here above tile 1, the front tile, and the other 3 plus 3, 6 at the diagonal. These are the only 3D connections. So you have many fewer 3D connections than you have connections in the second domain. That makes it rather practical for 3D technology where the vias, the silicon through vias, are actually relatively large across the planes than the wire width inside the planes. Okay. The move to front scheme now works such that the request is pushed out on the diagonal across the planes, and the reply comes back on the planes that are color-coded here. Okay? So this light green is one plane, this dark blue is the next plane, this green is the third plane, the dark blue is the next plane. The tiles on each of these planes get visited by one request at the same clock cycle. Okay? It's exactly the same mechanisms then in the 2D design, it's just now expanded into 3D. And it gets a little trickier to see this, of course.
You guys are actually going to build this stuff?
Yep. So we, how much can we say about the 3D?
Building formulas already.
I need to talk to my lawyer. Okay, so actually what we are building is 2 planes. Okay, just 2, not 4. At least. If it works, we'll see.
You'll come back and tell us about it.
Okay. The spider cache is particularly well suited for this new 3D technology because you have these tiles in the 2D plane on one die, okay? And then you have relatively few wires crossing the third dimension. Okay? So unlike all these other 3D proposals like fold a floating point unit across 3 dimensions, which requires many more wires per area within one die, this is a rather coarse-grained design. Okay? On top of that, as far as I know, this is the only design that can actually make use of the third dimension, namely by reducing the worst-case access latency from the square root in 2D of n tiles to the cube root. Okay? So from that perspective, this is the only thing that I am aware of that would make real technical use or quantifiable use of the 3D technology, if it then works. Other than, of course, doing mixed signal things and so on.
Does this third dimension asymmetry imply there's a difference in cross-section bandwidth if you cut at some weird angle? Or?
No, you don't see the tile. It's cutting it off for some reason. It's a white tile that the projection doesn't show. I can show it to you afterwards in more detail.
Anybody else have questions? I have one more question. In your very earliest slide, you showed a setup where you had a cluster of processors in the upper left-hand side, and then memory wrapping around them.
Let's try that again. Clicking technology.
Here we go. So, if you want the processors close to the average tile in memory, don't you want to put the processors in the middle? And was there a choice? Was there a reason for putting it in the corner?
So, very good question. Okay. Ideally, I would use a Archimedes spider in one layer of a 3D technology and put an H tree of processors in another layer and connect the root of the H tree to the spider. Okay? That would be nice. Now, 3D technology is not necessarily ever going to be economic, so the next best thing... oh, sorry. So, the next best thing is a 2D design. Okay, so what do you do in a 2D design? You want to have all processors equally close to your front tile. Okay, how do you do this? Okay, if you put all the processors in the center, where is your front tile? It's going to bias the access latency across the processors. Okay, I do not see the actual H-tree connection. You see the H-tree of the processor here. The design was supposed to show another connection from the root of the H-tree here down to Taiwan. Okay? Yeah, I'm sorry for the projection mess. Yes, so you will still have a latency here. If you take more cores, you increase the latency. If you put in just one core there, you reduce the latency and put the memory interface right next to Taiwan in the center. But you have plenty of opportunity to write many papers on different tweaks on how to lay that out.
Well, thank you very much. It's been very interesting.
I appreciate it. Thank you.
For more, please visit us at stanford.edu.